All right, so focusing again on the central question of series convergence. We've looked at the integral test, we've looked at the divergence test, we've looked at the limit comparison test, we've considered the p-series test, and now we're going to do something a tiny bit different with the alternating series. Okay, this is a sort of subclass of series that we'll consider. What is an alternating series? It's a series in which the signs of the sum strictly alternate. Okay, so you get factors that look like this. And what happens as k increases with these? You get minus 1, 1, minus 1, 1, minus 1, 1. Okay, so you get that strict alternation. Each term is the negative is the opposite sign of the previous term. Okay. So one example of this is the alternating harmonic series. And we have with the alternating harmonic series, we could express it this way. You could see it's like the harmonic series, but you get the alternating negative 1 there. And you'll have 1 minus 1 half plus 1 third minus 1 fourth plus 1 fifth and minus plus, on and on and on. All right, so let's discuss the alternating series tests. Okay, and just a quick note on notation here. We'll write alternating series this way, where this part here does not alternate. So AK is assumed to be strictly positive. Okay, and we're letting all the alternation happen with that factor. Okay, that's important. So here's a theorem. The alternating series converges provided we need to meet two conditions. Okay, the first is that the terms AK of the series are non-increasing in magnitude. Okay, they're non-increasing. So, the terms are positive, as we said before, and each subsequent term is less than or equal to the previous term. That's what non-increasing means. Okay, doesn't necessarily have to be decreasing, so you can get an equality, but it's less than or equal to AK for k greater than some index n. And again, what that means that greater than some index n is that the end behavior is what matters. Okay, so that's one condition, that you get non-increasing in magnitude. The second condition is that the limit as k goes to infinity of AK is 0. Okay, that's the second condition. So for series of positive terms, limit as AK goes to 0 does not imply convergence. Okay, remember with the divergence test we made a big fuss about that just because you get that the limit is 0 does not imply convergence. Now what could be confusing is that for our alternating series, as long as the terms are non-increasing, this limit does imply convergence. Okay, so you can positively conclude that a alternating series does converge when you do have this condition and the AK, that the terms are non-increasing. Okay, so that's a little bit confusing, but that's what's special about alternating series. When you have just pure positive terms, you're adding term upon term upon term. With the alternating series, you get to make as many subtractions as you make additions. And so that's where that sort of special character comes out, and why you can make stronger conclusions with that limit going to 0 with non-increasing terms. So what about the alternating harmonic series? Okay, let's make a statement about that. It converges. Even though the harmonic series, the good old-fashioned harmonic series without that alternating, diverges. And again, how could we conclude that? Well, it's clear that 1 over k is non-increasing. The terms actually keep decreasing, so 1 over a greater number is smaller, right? So the terms are definitely non-increasing. In fact, we can make a stronger statement, they're decreasing. And the limit of 1 over k as k goes to infinity is 0. And therefore, the alternating harmonic series converges. So let's look at a concrete example. Determine whether the following series converge or diverge. Okay, and so we have these different series. So let's tackle A. We have negative 1 k plus 1 over k squared. Well, AK again, AK, we take the alternating part out, and so we look at just the positive terms, 1 over k squared. That's clearly decreasing, and hence also non-increasing. And the limit of 1 over k squared as k goes to infinity is 0. Therefore, by the alternating series theorem, the series converges. Okay? Well, what about this over here? We need to express this in terms of k to get a grasp on it. First, notice that you do have the alternating behavior. And so the first term is positive, so you'll have a k plus 1 there, so that when you put in a 1, you get squared and, the next term becomes negative. If the first term was negative, you'll just use negative 1 to the k for when you start at k equals 1. Okay, and notice that this is just always 1 more than the previous. So this is the way to express, to give an explicit formula for the terms. Okay, so let's take the limit as k plus 1 over k goes to infinity. That's going to be 1. Okay, now you do have that alternating factor there. You don't have to consider that alternating. You could just consider that, and you'll get 1, and it's not equal to 0. And so the series diverges by the divergence test. So we didn't even have to go far there. We saw that this isn't even equal to 1, and so we just used the divergence test for that one. Okay. All right, that's that. And what about C? Here we have this over here, and we do have the alternating term. We start at k equals 2, but that's okay. We could always deal with a finite number of terms. And what do we need? We need that the terms are non-increasing. And is this non-increasing here? Are the terms non-increasing the positive parts? And they are. Okay, well, we could make that explicit by taking the derivative. And we find that the derivative is strictly less than 0 when k is strictly greater than e. And e is about 2.7. And so we do have decreasing for k is greater than or equal to 3. Now that's not k equals 2. But that's all right. A finite number of terms never changes the convergence or divergence. Okay, so we do have decreasing terms, that which means also non-increasing. Decreasing is a stronger statement. Decreasing implies non-increasing, but non-increasing does not imply decreasing. Moreover, taking that limit of the positive part as k goes to k goes to infinity, you use L'Hopital's rule, you get 0. Therefore, by the alternating series test, this series does converge. All right. So let's introduce some terminology, since we're talking about alternating series. The terminology involves absolute and conditional convergence. Okay? So these are definitions. If the infinite series with the absolute value of the terms, okay, and here this AK could be positive or negative. If when you take the absolute value of the terms, your series converges, this new series with strictly positive terms. If that converges, then we say that the original series converges absolutely. Okay. On the other hand, if after taking the absolute value, your series diverges, but without taking the absolute value of the terms, the series converges, we say that the series converges conditionally. So an example of a series that converges conditionally is the alternating harmonic series. Okay, if we take the absolute value, we'll just get 1 over k. Okay, and we know that 1 over k, the harmonic series, diverges. And so, on the other hand, the alternating harmonic series converges. And so, we say then that this series here, the alternating harmonic series, converges conditionally. Now, if you take a look at this, when you take the absolute value, you get 1 over k squared. And so, that does converge. And so, we say that this series here converges absolutely, okay? So we have a theorem that absolute convergence implies convergence, okay? If the absolute value of a series summed converges, then AK converges, okay? Absolute convergence implies convergence. If AK diverges, and then the absolute value will also diverge. And again, what is this telling you? Okay, absolute convergence implies convergence. Absolute convergence is stronger than convergence. Okay, why? Because now you're at when you have for a general series that could have negative terms, you get to slow down that sum. You get to subtract out terms. Okay, so if you take the negative values that could sort of slow down the sum, and you turn them to positive values and add them, if you still get a convergent series, well, then definitely the series with negative terms will also converge. Okay, so it's harder to absolutely converge. It's harder to take those negative terms, turn them positive, add them, and still converge. Okay, that does happen for series like this, but does not happen for the alternating harmonic series. Okay, and on the other hand, if a series diverges when it's easy, well, you better believe that it's going to diverge when it's hard. Okay, and so that's what that's telling you. So determine whether the following series diverge: converge absolutely or converge conditionally. So let's take a look at this. The absolute value of this is 1 over root k. That clearly diverges by the p-series test because p is equal to 1/2. That's less than or equal to 1. Thus, the series does not converge absolutely, but hey, it could still converge. And in fact, it does. 1 over root k is non-increasing, and the limit of 1 over root k is 0 as k goes to infinity. Therefore, the series does converge, but does not absolutely converge, and hence this series here is converges conditionally. Okay, it converges conditionally. What about the next example here? Well, taking the absolute value, get 1 over k to the 3/2. This converges because p is equal to 3/2 is strictly greater than 1. So this series converges absolutely, and so it definitely converges, and so you get absolute convergence there. You don't even have to make that other statement using the alternating series because absolute convergence is stronger. Okay. What about this term here? Okay. Well, when you take the magnitude of that, okay, then this is going to be less than, so sine of k is less than 1. Is the absolute value of sine of k is less than 1. That's where that's coming from, okay? So sine of k in general is between negative 1 and 1. And so its absolute value is going to be less than or equal to 1. And so we have this relation for the absolute value. And so doing the comparison test, if we know that this converges and this is less than or equal to 1 over k squared where p is equal to 2. So we know that this converges by the comparison test. And so sine k over k squared is absolutely convergent. And again, we don't have to do the alternating series because absolute convergence is stronger than just regular convergence. And what about this last one? Here, if you take the limit as k goes to infinity, you get 1, and that's not equal to 0. Therefore, the divergence test there will tell you that it doesn't converge even with that factor if we include it. So these terms, so this here will not go to 0, hence the series diverges by the divergence test. Okay, so we didn't have to sort of do anything trickier there. The divergence test helped us. So let's conclude by talking about the remainder in alternating series, okay? You'll recall that the remainder here is S minus Sn. So S is the sum of the infinite series, and Sn is the nth partial sum, okay? Let our infinite series be expressed this way: be a convergent alternating series with terms that are non-increasing in magnitude, okay? Let Rn be the remainder. Again, so this is what's left out, the terms that are left out beyond the nth term. Approximating the value of this series by the sum of its first n terms, okay? Then the remainder is less than or equal to the absolute value of the n plus 1 term, okay? Of course, we factored out the minus sign, so this should be positive. In other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term, okay? Before, for just regular series, we had to bound the remainder by taking the integral, if you'll recall. Here with the alternating series, it's less than or equal to the first neglected term, okay? And so that's a really cool result to have. Let's take a look at a concrete example. It turns out that natural log of 2 could be expressed with this alternating infinite series, okay? So it could be expressed this way. How many terms of the series are required to approximate natural log of 2 with an error less than 10 to the minus 6? Well, the remainder is basically, the bounds on the error, right? The remainder is what's left, what you didn't sum. It's the difference between the final sum minus the nth partial sum. So we have a bound that from our theorem that it's equal to an plus 1. Well, what is an plus 1? You just plug in n plus 1 where you see a k there, and you get this term here, and you want to take the absolute value of it, so that that sign there was unnecessary to write. So you get 1 over n plus 1. And so we know that Rn is less than 1 over n plus 1. So if we choose 1 over n plus 1 less than 10 to the minus 6, we're guaranteed that Rn would be less than 10 to the minus 6. So what does that mean when 1 over n plus 1 is less than 10 to the minus 6? We take the reciprocal, we get n plus 1 is greater than 10 to the 6th. And so whenever n plus 1 is greater than 10 to the 6th, okay, so if you go out, a million terms, then you know that the remainder will be 10 to the minus 6. Okay, so if you sum the first million terms and you get a number, you could write that the actual series is equal to that number plus or minus 10 to the minus 6. Okay, so it's within that bounds of error. Remark, we did not need the exact value of natural log of 2. So we didn't need to know what natural log of 2 is to know that after summing a million terms, the error in it is going to be less than 10 to the minus 6. Okay. Consider the series that you see here with the factorial, which could be written this way. Find an upper bound for the magnitude of the error and approximating the value of the series. So the actual value of the series is e to the minus 1 minus 1. Okay, that's the actual value. But we want to get an upper bound on the error if we use just 9 terms. Okay. So R9 here is equal to S minus S9. So over there you'll see an S minus S9. That's going to be less than or equal to the next neglected term, right? A sub 10. So taking the absolute value of the 10th term, again, we really didn't need that minus 1 to the power of 10 there. We're taking the absolute value. That's 1 over 10 factorial, which is about 2.8 times 10 to the minus 7. And so that's upper bound on our error. Okay, we're done with the problem. I do include an extra note there that the actual sum of the first 9 terms is negative 0.6321208111, as you see there, whereas the exact value, S is equal to e to the minus 1 minus 1, and that's its exact value. And the actual error is roughly 2.5 times 10 to the minus 7. Okay, so it's actually less than the bounds of our error. Our bound is 2.8, 10 to the minus 7. The error turns out to be 2.5 times 10 to the minus 7. But that's still good. I mean, what you need, especially if you start thinking about this numerically, right? You just want to calculate certain numbers numerically. You want a bound on the error, okay? That's what you're really after. And you know, knowing the error exactly requires knowing the value exactly. And we don't really need that often. We just need to know that we're within a certain bounds. And so that's how we could get our bounds using alternating series.